Okay, this is our last series video. So I'm on page 45 of your new BC unit packet. I didn't mean to say new, but the one with the BC topics is where I'm at. I'm on page 45. So make sure you find your packet and you're with me there before we get into this. So I just want to work through one more free response with you, and then your check for understanding, I'll pull it up in a minute and ask you to do a free response as well and see how we're doing on some of these bigger series ideas as we gear up for our exam coming up next week. So in this problem on 45, the function g has derivatives of all orders, and the Maclaurin series for g is provided for us here. In part A, we want to use the ratio test to determine the interval of convergence for this series for g. You should all hope and pray that we get a ratio test interval of convergence question next week, because these are pretty predictable in terms of series problems that can sometimes feel really unpredictable. So I hope that we get something like this when we are looking at this real exam next week. So let me set up my ratio test. That's the limit as n approaches infinity of the absolute value of the next term. So -1 to the n plus 1 times x to the, let's see, 2. I'm going to open up a parentheses here where the n was and put my plus 1 on the outside, and then I'll drop in the n plus 1 inside. That's what that one means for the next term. Same thing down here. I'm going to have 2 parentheses n plus 1 plus 3. There's my next term, and I need to divide that by the current term or multiply by its reciprocal, which is what I'll do. Put the 2n plus 3 on top, the -1 to the n on the bottom, along with the x to the 2n plus 1. So there's my initial ratio that I want to set up. Some things I can cancel right away, specifically because those absolute value bars are on the limit. Like the -1 terms are always going to be generating positive answers anyway. So I don't need to really worry about that. But before I cancel anything else, I am going to just go through the exercise of simplifying this a little bit so that I don't lose anybody in my canceling step. That x term right here in the numerator is actually x to the 2n plus 3. And if you're not sure about that, distribute up here, combine like terms, and then that's where you'll land. Down here in the bottom, I have, let's see, 2n plus 2 plus 3, so plus 5 in my denominator. I've got the 2n plus 3 up top, and in the bottom I've got the x to the 2n plus 1. So I just wanted to make sure I simplified that for a second before I went too far into this. And then the other piece that I want to make sure I take care of before I try to handle my limit is simplifying this right here, the x's. So in slow-mo up at the top, that's x to the 2n times x cubed divided by x to the 2n times x to the 1. That's where those sums and the powers are coming from. So when I see it like this, I can easily cancel the x to the 2n's, and I can go even further and realize that x cubed over x is just an x squared. So I'm going to take that simplifying that I did up there and pull out then the absolute value of the x squared term, because my limit is just dealing with n's. So the limit as n goes to infinity is really of 2n plus 3 divided by 2n plus 5. And thankfully, that's a nice limit. I just get 2 over 2 for that, or 1. So the resulting expression here is the absolute value of x squared times 1 from the limit in red. And for this to converge, I want this whole thing to be less than 1. So let's see. I've got a little bit of room over here. Let me see what I can come up with. That means x squared needs to be less than 1. Or -1, I'm sorry, because of the absolute value. So let me drop the absolute value and I'll be looking at this. That's a little bit better. And then if I square root, this is interesting. I'll square root everything. Let me just show you in slow-mo. I'll be looking at that. And I get x for sure in the middle. Over here, though, I'm a little concerned because I get an imaginary value. But when I square root that 1, I'm back to the plus or minus on that resulting radical. So I think my final inequality here is going to be sandwiched between -1 and +1 because of that square root of 1 term. Right here, when I square root that, I get the plus and the minus. So that's kind of interesting. But anyway, I want to now make sure that I take this and consider what happens at the endpoints. That's the last thing that I need in order to get my interval of convergence. I need to discuss what's happening at 1 and what's happening at -1. So let me scroll up where I have some blank room, and I'll say, oops, I'm still in the highlighter. Let's let x equal 1. That means my sum from 0 to infinity is of -1 to the n. I'm going to replace the x with a 1, so that's 1 to the 2n plus 1 all over 2n plus 3. And let's see, 1 to any power is just 1. So this whole term right here is just 1. That's not super scary. It kind of disappears. So the sum that I'm interested in is the one that goes from 0 to infinity of -1 to the n all over 2n plus 3. So the fact that the -1 to the n is in the numerator means this is alternating. So if you want, you can think about a few of the terms here just to visualize the series and what's happening. If I plugged a 0 in, I'd get 1 over 3. If I plugged a 1 in, I'd get -1/5. Then I'd get +1/7, etc., etc., etc. So I can look at this and I can see that yes, my terms are alternating. Check. The magnitude of the terms, the 1/3, 1/5, 1/7, those are decreasing. And the terms have a limit as n goes to infinity that heads to 0. Check. So by the alternating series test, at the endpoint of 1, I have a convergent series, which means I get to come all the way back down here. Hold on. And at 1, I want to make sure that I include that endpoint. I'll test out what's happening at -1 as well and see if we can close out. So when x is equal to -1, I get a different series, still from 0 to sorry with the emails. That's an infinity up top. I get -1 to the n times -1 to the 2n plus 1 all over 2n plus 3. So when x is -1, it looks like I'm generating common bases up there in my numerator. Both of those bases have that -1 in common. So in algebra, that means I can add up my powers. I get -1 to the n plus 2n plus 1 up top, all over 2n plus 3 in the bottom. Simplify a little bit more. Let me actually grab an eraser and get rid of some of this so I have some more room. I'm just going to add that stuff up in the power, and I get, let's see, -1 to the 3n plus 1 all over 2n plus 3. And this is from 0 to infinity. Okay, so I need to think critically at this stage about the term up top. That's -1 as a base, but the power is 3n plus 1. So I'm going to think about that. What happens up top when I take -1 and raise it to given powers? For example, if I plugged a 0 in, I would have, let's see, -1 to the 1 power. So the first term here would have a numerator of -1 and a denominator of 3. If I plugged a 1 in, I'd get -1 raised to the 3 plus 1 to the 4th power, which generates +1, all over 2 times 1 plus 3, a 5. One more, if I plug a 2 in, the power up there becomes 7. -1 to the 7th power is negative. And I get a 7th down here. It looks like the only change that's occurring when I check the other endpoint is that my alternating terms are opposite. So it used to have a +1/3 to lead, and now I'm leading with a -1/3. So the good news is this is still alternating. And based on the work that I established over here in my previous endpoint, all that stuff still applies to this series. The terms alternate. The terms are decreasing, the limit approaches 0, so this endpoint also converges, which means I get to come down to my interval and include that one as well. Gosh, what a doozy. That's a tough question, but we can do all that work with the ratio test, and we just have to dig in really carefully when we check our endpoints to make sure that we're closing out and getting the correct final answer. All right, so here's part B. The Maclaurin series for G evaluated at x equals a half is an alternating series whose terms decrease in absolute value to 0. The approximation for G of a half using the first two non-zero terms of the series is 17/120ths. Show that this approximation differs from the true value by less than 1/200. The key here is that the approximation that's given has been created with two terms. So they are taking this series and using A1 and A2 to get this approximation. What this is arriving at is that like A1 plus A2 is 17/120ths, and that's the approximation that they've generated for the G of 1/2 that's being given. Because this is an alternating series that converges, I can get the error associated with that approximation, by just using the third term of the sequence. Since I have an approximation that was created using two terms, the error is always going to be bounded by the third term. So let's see. The third term here is x to the 5th over 7. I want to make sure I'm right about that, so let me toggle back over here. Yeah, I'm using this term right here, that one, the x to the 5th over 7 at 1/2 in order to generate my error bounded, because this is an alternating series. So x to the 5th, that's going to be a half to the 5th over 7. Well, 1/2 to the 5th, I promise, is 1/32 over 7. That's 1/32 times 1/7. I hope you trust me, but that's 1/224, which is awesome because that number, 1/224, is less than 1/200. So by showing the computation of the third term, we are proving that our approximation differs by less than 1/200. Kind of neat and deceivingly easy for something like this. So interesting to make a note about that. Okay, so here's the last part of the problem. Write the first three non-zero terms in the general term for G prime. So I went ahead and recorded G again, and this question basically just wants me to differentiate everything and generate a function G prime. So the derivative of x over 3 is 1/3, minus the derivative of x cubed over 5 is 3x squared over 5. Plus the derivative of x to the 5th over 7 is 5x to the 4s over 7. And that's going to extend along for a while until I get to the general term. You can do this two ways. You can try to like gauge a pattern over here and then use like your conceptual understanding to build the relationship. Or you can come over to the original general term and just try to differentiate that, which I actually prefer. It all kind of falls in line eventually. So what I mean by that is the -1 to the n is just a constant, as is the 2n plus 3 down here. So the derivative would only need to be taken on the x to the power, and the power rule states that you get to bring the power down and then subtract 1 from the power. So 2n plus 1 minus 1 actually just gets me a power of 2n. And that, if you'll notice, generates everything that I have over here to the left. If I were to substitute in a 1, a 2, a 3, etc., I would get all of the all of the terms over there. And actually, since our summation started at 0, I'd have to start with 0, but then everything works out just fine. So that was a really intense free response problem. Check the email that I'm attaching this link in for the problems that I want you to attempt now that you've had a little bit more practice with this stuff. And I will see you in tutorials on Friday. Thanks.